Hey guys, so today I wanted to start with our introduction to fire, arson, and explosives, right? I think that this is the only set of notes for this unit. It's a fairly short unit. We should be through in about a week and a half, maybe 2 weeks, but it's pretty exciting. So let me turn off my camera and let me get started with your presentation. Okay, so this is going to be chapter 14 in your book. So if you wanted to take a look and see where that's going to be or where all this information is coming from, you have access to the online book. So please make sure that you do that. Okay. The next slide, I'm actually going to show this in class before the unit today, but I've put it in here in case you want to watch it for yourself. It's basically how fast a Christmas tree can go up in flames if it's not watered. Okay, so let's start with this introduction. So when we talk about arson, arson investigations are often very complex and difficult circumstances, right? And it's usually due to the person that has committed the crime thoroughly planned it. Nobody just says, hey, by the way, I think I want to go start a fire and I'm going to go do it, okay? So a lot of times the perpetrator has already thoroughly planned it and is not present during the fire. So the destruction is extensive. So when we talk about what the criminalist function is basically they want to detect and identify the relevant chemical materials collected at the scene. And then the other big thing is they want to be able to reconstruct or identify the igniter mechanisms. How did the bomb or why did the bomb catch on fire? What pieces can I find at the crime scene so I can rebuild it, which may give me some idea about the bomber's identity. A big thing about chemistry, right, is there's a huge fire component. So a lot of you guys will probably remember some of this stuff from your physical science class, maybe even your Earth Systems class Earth Science class in 6th grade, if you can remember that far. So in terms of the chemistry of fire, fire is going to be a type of oxidation. Oxidation basically means that you have some sort of hydrocarbon that's in the presence of oxygen, and we produce new substances based on that chemical equation. To start a fire, the minimum temperature that is needed to ignite the fuel spontaneously is known as ignition temperature. For this unit, there are going to be a fair amount of definitions, so it would probably be a good idea that you write down some of the terms as we're going through the lesson. The heat that's involved when a substance burns is going to be known as the heat of combustion. Some of the other things that are going to affect the chemistry of a fire are going to be the rate or speed at which that oxidation reaction happens, and then what kind of fuel. Okay, so usually your fuel is going to achieve a reaction rate with oxygen, right? And it's usually sufficient enough to produce a flame, but only when it's in a gaseous state. So we'll talk about what ignites in the room when there's a fire going on and how it works. Some other definitions is we have the liquid that burns with the temperature is high enough to vaporize it. So if we have some sort of liquid and it burns hot enough that it turns it into a gas, okay, that is called the flash point. If we have a solid that it is so hot that it decomposes into a gaseous product, then that's called pyrolysis. And then we have glowing combustion. And that basically is burning at the fuel-air interface. Something like that would be seen if you were smoking a cigarette. Hopefully none of you guys smoke cigarettes. But right at the end where the butt is lit, that's where you will see that glowing combustion. The other phenomena is known as spontaneous combustion. Some of you guys have probably heard of a CSI episode where they were trying to figure out if some dude bursts up in flames on its own. It is very rare, and it usually happens because of some natural heat producing process, and we are in an area where it's not very well ventilated, or in containers that are not very well ventilated. Okay, when a fire happens, it is going to produce heat and light, right? Those lights are seen as flames. To initiate and sustain combustion, and these are the trifecta, the big three. One is a fuel must be present. 2, oxygen must be available in sufficient quantities to combine with that fuel that's present. And that heat must be applied to initiate combustion. And of course, you have to have enough heat that's generated that sustains the reaction. So some of the basics, a fuel is going to achieve a reaction rate with oxygen significant to sustain a fire only when it's in the gaseous state. Now, in terms of heat transfer, these are probably 3 methods that you guys have studied at some point in your science career. So the 3 mechanisms of heat transfer are going to be conduction, radiation, and convection. Conduction is going to be the movement of heat through a solid object. There's a hot pan on the stove that you've just taken off the stove, or maybe a pan that you've just taken out of the oven, and you end up touching it with your hand, right? The heat transfers from that hot item directly to your hand, and then you get burned. Radiation is going to be the transfer of heat energy by an electromagnetic source or radiation, and that is going to be something like the sun, a campfire that you're sitting next to, that you can feel the heat, but obviously you're not getting burned. The third is going to be convection, which is going to be the transfer of heat energy by movement of molecules within a liquid or gas. This happens a lot in when we microwave our food. So like a microwave is also known as a convection oven, right? The other thing is you can think about it like if you're boiling a big pot of spaghetti, you get that boiling water moving and hot, right? And it's boiling, and that boil or that energy that's coming off is going to basically break down and cook your food. Okay, so those are 3 main examples. Now, when we talk about what's specific to a fire scene, so the arson investigator needs to begin by examining a fire scene for signs of arson, and typically it needs to be as soon as that fire is put out. Obviously, we want to check for, structural issues. We don't want the building collapsing on anybody, but as soon as the arson investigator can get in there, that is the best time for them to start. So when we talk about accelerants, right, that speed up the burning of a fire, a lot of them are going to be petroleum-based accelerants. Big one is going to be gasoline. And then the necessity to begin an immediate investigation, right, takes precedence over a warrant, which means that the arson investigator doesn't need a warrant to go in and search the scene, right? It's kind of like if a cop were knocking outside the door and they heard a gunshot, right? That is immediate entrance into a building or a residence, right, without a warrant. It's the same thing with a fire, right? The fire is that we just had a fire and it is an extreme emergency and I don't need to wait for a search warrant. So the first thing that the fire investigators going to want to do when they get to the scene is see if there is some sort of origin, which is basically where the fire started. The origin, usually if it is an arson scene, will usually have some sort of accelerant or some sort of ignition device, but that's always where the arson investigator wants to start. Now, what is the fire investigator looking for when they get to a crime scene? Well, there are a bunch of burn patterns and phenomena that I would like you to be aware of. So the first one is going to be a V pattern. This normally indicates where the fire starts. If you look along its back wall, where this number is, could be 503, maybe 603, right? You see a black V right next to it, right above the couch. That is considered a V pattern. The next one is going to be alligatoring. So if you look at this material up here, it looks like alligator skin. So that's why they call it alligatoring. What happens is the material burns so hot that it's going to acquire these raised blisters on the surface. Okay. The next 2 are going to be pore patterns and crazed glass. So for pore patterns, there's going to be some sort of pool of ignitable liquid, and it leaves some sort of irregular pattern on the floor. If the arson investigator is looking for an accelerant, they might take a look at that to see if there's a particular pore pattern on the floor where the person basically put the accelerant to start the fire. The other one is going to be crazed glass. That's rapid cooling of glass, and it usually causes very, very small fractures. The next 2 are big. So we're going to have the spalling of concrete. So under intense heat, there are going to be parts of the concrete that are going to fail. The other one is flashover, meaning there's some sort of spontaneous ignition without a spark or a flame. And then the next 2 are the last 2. One is going to be backdraft. There's a great movie named Backdraft about some Firefighter, so if you haven't seen it, maybe you should. It's a real old movie. So backdraft is going to be the sudden increase in oxygen after the fire starts that was extinguished. So this is an example of a firefighter may go in, and in the movie, there's actually a scene where I guess the firefighter didn't realize that they had put out the flame and closed the doors, basically to seal off the area to not let oxygen back into the area, because oxygen is going to reignite the flames. Well, one of the firefighters opens that door that wasn't supposed to be open, and then there's a huge explosion, and then you see the backdraft. Okay, very difficult situation. You obviously can injure some of your fellow firefighters, or if you're trying to get to somebody that may be stuck in the fire, that may cause some additional problems. The last one is going to be rollover. So when you watch a fire, and especially when we watch the Christmas tree fire, there are going to be gases that are going to be igniting, and they're going to rise, and it's going to look like the ceiling is on fire. Okay, that's what would be called rollover. Now, when we talk about just a regular fire, and then we talk about arson fires, there are certain things that may be indicative of an arson scene, meaning the fire was set on purpose. So there are some of them that are spurious, meaning that it could be or it might not be. So the first one is going to be alligatoring. Alligatoring doesn't mean that the fire was set on purpose. Neither is a narrow V pattern. A lot of people think that a narrow V pattern indicates that there is more accelerant, so it burned faster in that spot, which is what narrowed the V pattern. That's not always the case. Crazed glass, pour patterns, spalling of concrete, and melted metal are also the rest of the spurious arson indicators. In terms of the true arson indicators, there are 7 of them. If there are multiple points of origin, there is no fire that I've ever heard of that starts by accident in 4 different places. Okay, it just doesn't happen. Trailers, that means that somebody spread out combustible material to make the fire spread faster from place to place. If there is an ignition device, most of the times it's not accidentally there. If there are evidence of other crimes, maybe there's a body you find at the crime scene and they were trying to burn down the house to hide the evidence of the body that they killed. If you see gasoline containers chilling in the room, so if you see like accelerant containers, then that's probably not an accident. Eyewitness, somebody saw them light the fire, and if there's any kind of excess or any kind of ignitable liquids chilling that wouldn't normally be there, it'll be a problem. So like if there's gasoline in the garage and it's on fire, okay, that's plausible that somebody could have a gasoline tank in their garage. But if they have a gasoline tank in their living room, it's probably a little less likely. Okay. Now I want to talk a little bit about victims of fire and what you see. So you may see some carbon monoxide poisoning, and in that case, you would have to actually do an autopsy. You can't just look at somebody and know that they have carbon monoxide poisoning. What actually happens is when you start to look at the organs, all their organs are pink. And the reason that they're pink is because normally your body carries oxygen, but carbon monoxide has a higher affinity for your cells. It likes those cells better than oxygen, so they kind of trade places. Carbon monoxide is what turns all of the inside organs pink. The other thing is going to be presence of soot. There may be soot in the lungs if they were alive when the fire started. Pugilistic posture means that they just look all curled up, like they look like they're ready to fight, right? And that's just because of the intense heat that's kind of contorted their body. There are all sorts of fire-induced injuries. Pugilistic posture can cause breaks in the joints. So you want to make sure that if you're a medical examiner and you're looking at a body from a fire, that you don't assume that that could have been the cause of death, because it could have just been caused by the actual fire. The muscles can contract severely enough to break bones. The fire is so hot that the skull can fracture. There are a ton of other injuries that victims of fire can have that the medical examiner kind of has to wade through. Okay, so in terms of a fire scene, normally a fire has a tendency to move in an upward direction. So the probable location of origin is probably going to be the lowest point. And you're going to look for the most intense characteristics of burning, because that's probably where the fire started. Fortunately, combustible liquids are really never completely consumed during a fire. So there will always be some sort of evidence if there is a combustible liquid that you'll be able to use. Okay, let's talk about collection. So when we get to a scene, there are certain ways that you're going to collect things. So at the point of origin of fire, you can find all sorts of things, ash and soot, along with some porous materials that could contain some excess accelerants. These all need to be collected and stored in an airtight container. I don't know if you guys remember from the first time that we talked about how to package evidence, I talked about glass containers. This is one of the scenes where you may want to use glass containers because glass is non-reactive. So if you have something in there that might potentially blow up, I don't want it to be able to react with the container I put it in, because then everybody's going to be sorry. Okay. Let's continue with collection. So you can collect the traces of the flammable liquid, and there is a particular collector known as a vapor detector, which we call it the sniffer, okay, which you can actually collect some of those residues and keep some of that vapor so that you can put it through your gas chromatography machine. It is also important that you need to take a sample of similar but uncontaminated control specimens if they are there. And obviously you want to search for igniters, matches, sparking devices, parts of a Molotov cocktail. For those of you that might not know what that is, it's basically a glass bottle that has some sort of fabric in it, that it has some sort of ignitable liquid in the bottle, and it's kind of a wick that I shouldn't explain to you how a Molotov cocktail works. Anyway, you light it, it explodes. You light it, you throw it, it explodes. Okay. Now, in terms of fancy equipment, there's only one piece of equipment that's really a big deal for arson. And we're going to talk more about this when we get to the drug unit. But the first one is going to be gas chromatography. So in the lab, the gas chromatograph is going to be the most sensitive and reliable piece of machinery to detect flammable residues. We'll talk more about the process a little bit later on in the unit, just so you can understand how it goes. But a majority of the arsons are going to be petroleum distillates. So we're talking about gasoline, we're talking about kerosene. What the gas chromatography machine does is it separates the different hydrocarbon components, and it produces, let's just say, a visual pattern or picture of that particular petroleum product. And every type of petroleum product has its own what we call snapshot, what it looks like in the gas chromatography machine. So if I were to run a sample of known gasoline and put it up against the sample at a crime scene, based on the gas chromatography results, I should be able to say, yo, that's gasoline for real. This is gasoline now that I have identified from my crime scene. So by doing that comparison, right, a forensic analyst will be able to identify the accelerant used as long as we have it on file or have that chromatograph picture on file, okay? That is actually the end of the arson notes. So I hope that that was helpful, and I will catch your act later.